It's my pleasure to introduce today Ofir Nachum, who is a senior research scientist at Google Brain. Ofir's work really spans a variety of topics ranging from hierarchical RL to off-policy learning and policy optimization. And more recently, Ofir has been pushing some new techniques in the field of reinforcement learning. And really, I've been waiting for this talk for more than 6 months, actually. It's a topic that I really want to learn more about, this topic of convex duality and how optimization can better inform us in the design of better algorithms in RL. And this is really something that I admire in Ofir's work, the ability that he has to take theory, but not only just do theory for the sake of doing theory, but also doing theory for building up better algorithms. And his work really shows that he's able to bridge that gap from theory to practice. And so Ofir's talk is being recorded, but Ofir is with us. And as usual, you can always post your question in the Q&A feature, and Ofir will take questions after the talk. So thank you.
Let's say you have a policy and you have this environment. What is the expect? All right, so hi everyone, I'm Ofir and I'll be talking today about reinforcement learning via convex duality. So let me get started at a very high level, just get our foundations down and get our notations aligned about reinforcement learning. So we already know this, but just to get our notation aligned. So in reinforcement learning, we have this setting of a policy acting on an environment. Well, the environment is usually in the form of a Markov decision process. So at every episode, you begin by sampling some initial state from some initial state distribution, which I have here as mu0. And then the policy successively chooses actions. And at each step, you take your state and action, and that somehow yields an immediate reward given by this reward function, and transitions to a next state given by this transition function. And in reinforcement learning, so we usually know what the policy is, and we see the states and actions and rewards, so all this stuff in blue, but we don't know explicitly what the initial state distribution is, or what the reward is, or what the transition function is. And generally, there's a lot of questions we might hope to answer. Here are the top two that are most popular in reinforcement learning. So the first is policy evaluation, which asks, okay, let's say you have a policy and you have this environment. What is the expected value or average reward of your policy? And then one step further is this policy optimization. So given that you want to maximize your value, what policy should you choose to act in your environment? And in reinforcement learning, usually when we think about algorithms to answer these questions, those algorithms mostly fall under the wide range of dynamic programming approaches. What this means is, for example, if we think of the policy evaluation question, policy evaluation, the standard algorithm for doing that is via expected Bellman backups. Right, so this is a sort of dynamic programming algorithm where at each step you back up your Q values to set them to be the immediate reward plus gamma times the expected next Q value. So this notation here that I'm using of a P pi, you can think of it as this expectation over next Q values. In matrix form, it looks like this. So you can imagine Q is just a big vector with an entry for each state and action. The rewards are also a vector. And then this P pi, you can think of it as just a matrix. And indeed, because it's an expectation, it is just a linear operator. And you can write it in the simplified form. And we all know that this dynamic programming procedure, if you do it a bunch of times, it's going to converge to the Q pi values, and that's going to be the answer to the policy evaluation question. Similarly, if we talk about algorithms for policy optimization, most of those also fall under dynamic programming. So one is actor critic, where we first do dynamic programming backups to find our Q pi, and then we update our policy pi using this policy gradient, which says that the gradient that you should follow for pi is just the expectation under the on-policy distribution, which I denote here as d pi, of q pi times grad log pi. So that's actocritic. Alternatively, the other major reinforcement learning algorithm for policy optimization is stuff like just standard Q learning. And that, again, is also a form of dynamic programming because it's just another form of successive backups. Only this time you don't have an expected p pi backup. Instead, you have a max backup. And note that although I wrote it as if it's a linear operator, it's actually not in a matrix form because there's a max inside. Okay, so that's the background, which we're all familiar with, but just to align ourselves. Now, what's this talk about? So this talk is about convex duality for reinforcement learning. What this means is that instead of answering these reinforcement learning questions using dynamic programming, I'm going to introduce an approach to RL based on convex programming. By convex programming, I mean we're going to frame either policy evaluation or policy optimization as a convex problem, and then we're going to apply the tools of convex duality and convex optimization to solve those problems. Now, the first question you might have is, why should we care about this? Because we already have a bunch of algorithms based on dynamic programming. They all work pretty well. We're all pretty familiar with them. Why should we care about this approach using convex programming? And there's a number of reasons. So the first one is that although these dynamic programming-based algorithms are ubiquitous, they're a result of very rough approximations, right? So if we think back to the original backup procedure of policy evaluation or policy optimization, it mostly makes sense in a tabular setting where you have finite states and actions. When you're not in a tabular setting, when you need to use function approximation, when you're not in a finite state and action space and you only have access to stochastic samples of your transitions or rewards, then things are just a series of very rough approximations. So actocritic is the result of rough approximations, and when you go off policy, you lose a lot of the theoretical foundations that actocritic is under. And this is a recurring theme in dynamic programming-based approaches to reinforcement learning, that theoretical guarantees outside of simple tabular settings are very hard to come by. And so by using convex programming, we hope to be able to leverage a lot of the existing results in convex optimization literature, right? Because convex optimization is full of results that tell you, given that you have a convex problem, how do you optimize it in stochastic settings? How do you optimize it in function approximation settings? And how do you relate the approximation error in your function approximation space to the optimization error to get a final error on your final result? And so by using convex programming, we're going to hope to leverage all these existing results to get better convergence guarantees and get better algorithms. And lastly, convex duality will also enable lots of these off-policy algorithms, which are not just a result of very rough approximations. We'll actually be able to understand what the off-policy in a convex optimization perspective. Okay, so that's the hope, and that's the why. And now we can actually get started. So here's the outline of my talk. What I'll start with is a very quick and basic introduction to convex duality, and specifically just all the things we need to know for our talk. The first is just what is a Fenchel conjugate, and then I'll talk about Fenchel-Rockefeller duality, which you can think of just as a generalization to the well-known linear programming duality. Once we have those down, I'll then talk about how we use these concepts in reinforcement learning. So I'll start with the QLP, which is a linear programming specifically for policy evaluation, and I'll show how we can convexify it and use it to get very nice off-policy evaluation algorithms, and then one step further and show how to use that same QLP for off-policy optimization algorithms. After the QLP, I'll introduce the VLP, which is a more streamlined and direct linear programming specifically for policy optimization. And then I'll show, same as for the QLP, how do we use the VLP to get a nice off-policy optimization algorithm. And then lastly, I'll talk about how we can use Lagrangian duality to get even better guarantees. Okay, so with that, we can get started. So let's start with the basics of convex duality. So the most perhaps important and basic concept in the field of convex analysis, and specifically how we'll use it, is this idea of a Fenchel conjugate. Fenchel conjugate refers to a specific function f. So let's say we start with some function f that's given to us. We define its conjugate, which I have here as f star, as another function, which is the result of some optimization. So f star of a given argument y is going to be an optimization over x of x times y minus f of x. And you can mostly ignore this omega. It's just the domain. It's just going to be the domain of f. Okay, so given a function f star is going to be its Fenchel conjugate, the result of this optimization problem. Here's a simple example, perhaps the simplest example. So let's say our chosen f is the square function, 1/2 x squared. Then how do we solve this optimization for a specific y? Well, it's pretty easy to see that the optimal x here is going to be x star exactly equal to y. And once we plug in x star equal to y, we get y squared minus 1/2 y squared, and that's just going to leave us with 1/2 y squared. So when our original function f is the half square function, its conjugate is also the half square function. So that's a simple example where this optimization has a closed form. And there's a bunch of other functions f where f star can be written in closed form. So here's that. For a simple example, a square function. Here's a generalization of that to general polynomials. I want to point your attention to this row. This row refers to the indicator function, which will end up being quite useful for us. So the indicator function here says, with respect to a specific a, it checks if its input argument x is exactly equal to a. So if x is equal to a, it's going to output 0. If x is not equal to a, it's going to output infinity. Right, so it's just an indicator function that checks, is my input x exactly equal to a? And the interesting thing about this indicator function is when you solve this optimization, you can solve it in closed form and you just get a simple linear function where the coefficient in the linear function is exactly this a. Here's another interesting function, the f divergence. So when you think of an f divergence with respect to a specific reference distribution p, so p is fixed and x, this other distribution, is your input to your function, then the conjugate of that can be written as well in closed form as the expectation over your reference distribution of the conjugate of f. And you can see also in the last row, there's a KL. So in the specific case of the KL, you actually get a log expected exponent, which is also pretty nice. So these are a bunch of closed forms. And then the first neat duality result is the following. So if your function f, if you start with a convex function f, then the conjugate of the conjugate is the original function. Right? So there's this nice duality between f and f star in the sense that you can write f star as this optimization, and the duality tells you f is can also be written using an analogous optimization with respect to f star. What this means in our table here is that the columns here go both ways. So like the conjugate of the linear function is the indicator function. The conjugate of the expected f star of y is the f divergence with respect to that distribution you used in your expectation. So that's a neat little duality result. And then the more general version of that, and what we'll find the most useful, is Fenchel-Rockefeller duality. So Fenchel-Rockefeller duality starts with the following optimization problem called the primal problem. So let's say you're trying to minimize this quantity, which is the sum of two functions. One is f of x, and another is g of ax. So x you can think of as some vector, and a is like a matrix. So this is a matrix multiplication of a and your vector x, and you're trying to minimize this. So for this primal, Fenchel-Rockefeller duality says that there's a corresponding dual where you're maximizing, in terms of some y, the following quantity. And we can see f becomes f star, f conjugate in the dual. G in the primal becomes g star, g conjugate in the dual. And then the a that used to be inside of g becomes an a star inside of f star, where a star is just my notation for the transpose of this original matrix. Right? So you can already think that this might be useful if, for example, optimizing for when a is inside of g is hard, but optimizing when a star is inside of f star is easier. And so we can switch between these two. And so in general, you have this weak duality, but the more interesting duality is that if f and g are convex functions and some other mild condition, then the results of these two optimization problems are exactly equal. And moreover, once you've solved one of these, you can actually derive a solution to the other. So if you've solved the dual and you have this y star, then you can get an expression for a solution to the primal in terms of this gradient of the conjugate f. So to put this in sort of perspective of things you might be familiar with, you can think of Fenchel-Rockefeller duality as a generalization of the LP duality of linear programming. So LP duality is specifically realized if you take f to be this linear function with respect to some coefficient c, and g to be an indicator function. Right, so the primal then looks like this. So g, by making g the indicator function, we're explicitly constraining ax to equal b, exactly. Right, because if ax does not equal b, then this g is going to be infinity, and then you've certainly not solved the optimization. We're not at the optimum. So ax must equal b to make the indicator function 0. And then the f of x is just going to be the linear optimization. So we're going to try to minimize c times x subject to this constraint. And now when we look at the dual, so first looking at g, so g in the primal becomes g star in the dual. So originally we had an indicator function, and we know the g star, the conjugate of an indicator function, is the linear function. And so that's how we get this, linear function in the dual optimization. On the other hand, f in the primal becomes f star in the dual. And we started with f being a linear function. The conjugate of a linear function is the indicator function. And that's how we go from f being in the objective here to f being in the constraint here. And we can see how a switched places from being inside g in the primal to now being its transpose in f star. Okay, and Fenchel-Rockefeller dual just recreates the LP duality, which tells you, okay, these problems are equivalent. If you've solved one, you've solved the other. Okay, so that's all the convex duality you will need to know. Now, where's the reinforcement learning? So the nice thing is that many reinforcement learning problems can actually be expressed as linear programs. So here's an example of, let's say we want to do policy evaluation. How do we solve it in terms of an LP? So here's an LP, and you can see the variables I'm optimizing for are Q values. And my constraints are just the constraints from the Bellman backup operator, right? So this constraint says for any state in action, the Q value should be at least the immediate reward plus gamma times the expected next Q value. Right, so these constraints constrain your solution space to have all the Q values be at least Q pi. And then this objective here, this minimum objective, is going to push all those inequalities to be exact equalities. So once you've got exact equalities here, your Q star is exactly Q pi. And once you plug in Q pi in here, you see, okay, this is just the expected initial Q values. And the expected initial Q pi values are exactly the policy value. Okay, so this is a sort of linear programming instantiation of that dynamic programming policy evaluation algorithm I mentioned at the beginning. So for this primal problem, we know there's an equivalent dual form. And the dual form looks like this. So instead of Q values, now we have these D values. And these D values actually correspond to a distribution. Specifically, the distribution is going to end up being the on-policy distribution for pi. And we can see that from looking at the constraints, actually. So the constraints here, instead of the Bellman operator, we have what's called the transpose Bellman operator, which is not as common, but it is known. And specifically, it specifies the sort of stationary property of any Markovian distribution, in the sense that if we think of D as a distribution, then this sort of says the flow out of state S in action A at any time should be equal to the flow in. Well, the flow in either comes from this constant source at the initial states and actions, or it's coming in from the transition operator. Okay, so these constraints specifically constrain D to be exactly D pi. And then once we stick D pi into this objective, we just get the expected reward under D pi. And that exactly is the policy value. So this LP is known as the QLP, right? Because those Q values. And now we can think about, okay, given that we have these nice LPs, how do we actually solve them using convex optimization? So we can hope to solve them directly, but we quickly run into issues, mainly with these constraints. Whether you're in the primal or the dual, the LP is going to have a constraint for each state in action. And it's hard to satisfy all these constraints in stochastic, function approximation, offline settings. And that's the big issue with solving these LPs either in the primal or dual forms directly. And so our insight is going to look at the generalization of LP duality. So we're going to look at Fenchel-Rockefeller duality, and we can realize that if we look at the dual of a constrained strictly convex optimization, so if we switch the linear objectives here to some convex objectives, then we're actually going to be able to get a dual that's unconstrained. And so what we'll do repeatedly in this presentation is we'll just take one of these LPs, we'll add a strictly convex regularizer to them, and then use Fenchel-Rockefeller duality to yield a more tractable problem. Okay, so that was a lot of words to describe what's coming up. So hopefully in the next few slides, all that will make more sense. So let's look at a concrete instantiation of that general method I described, looking at policy evaluation. So we can start again with these LPs. We have the primal form in terms of Q values. We have the dual form in terms of stationary distributions. And we can remember, okay, the big issue is the constraints. Now, let's take a closer look at this dual LP. So we can look at these constraints and realize there's actually a constraint for each state and action. And there's a variable for each state and action. And so this LP is over-constrained in the sense that these constraints actually uniquely determine what D star is, regardless of what the objective is. And the nice thing is, once we have D pi, we can compute the value of the policy. We can just stick it into this objective. And so what we're going to do is we're going to change this objective. Changing the objective won't change the solution, but changing the objective will change what we can do with convex duality. And so we'll change this objective, apply convex duality, and that'll yield us an easier, more tractable problem to solve for D star, which is D pi. So specifically, we can replace that original objective with this convex objective. Specifically, we take this F divergence with respect to some fixed reference distribution. So this D superscript D is just a fixed reference distribution. The notation might be a little confusing, but this is not a part of the optimization. We're still just learning D, and this is just a fixed reference distribution. Now, although we've changed the objective, the optimal D star is still D pi, because we've still got all these constraints which uniquely determine what D is. But the difference now is when we apply convex duality, we're going to end up with this unconstrained problem. Let me show you how we got that. So if we recall, Fenchel-Rockefeller duality needs an optimization problem in this form, the sum of two convex functions. So in our case, this H is going to be the F divergence. This G is going to be the indicator function, right? So G here is going to replace the constraints. So G is going to enforce that these constraints are satisfied. And these constraints are satisfied when you take this matrix of gamma p pi minus I, when you multiply that with D, it must be exactly equal to 1 minus gamma times this initial state and action distribution. Okay, so we've got this original problem in this form, and now when we apply duality, this H becomes H star. So we started with the F divergence. The conjugate of the F divergence is the expectation under that reference distribution of the conjugate of F. So that's how we get this expectation here with the conjugate of F here. Similarly, G in the original problem becomes conjugate of G in the dual problem. And the original G was an indicator function. The conjugate of an indicator is a linear function. And in our case, that linear function is just 1 minus gamma times the expectation over the initial state and action distribution. And then lastly, A in the original problem becomes A star or A transpose in the dual problem. And so when we apply A star to this original gamma p star pi minus I, we just get back the standard transition operator gamma p pi minus I. And so that's how we end up with this sort of Bellman residual inside this expectation over the reference distribution. Okay, now what's good about this problem? Well, the nice thing is there's no longer any constraints. So the constraints we had before in our original problem were converted into these penalties. Secondly, these penalties are applied over this expectation, which is very good for stochastic settings. And specifically, this expectation is over the reference distribution. And we have a lot of choice in what this reference distribution is. No matter what the reference distribution, you can still apply this technique. And in our case, where we're doing off-policy evaluation, the most convenient reference distribution is just whatever distribution we have access to. So whatever our replay buffer is, whatever our log data set is. And so that's how we get this nice off-policy objective. Okay, so we have this nice problem, nice dual form, where it's an off-policy expectation, it's unconstrained. And moreover, so what we cared about was, in our original problem, finding this d pi, which was the solution to the original problem, d star. And if we remember from French-Rockefeller duality, it tells us, given that if we've solved the dual problems, or if we've solved like q star, then we can get an expression for d star. And specifically, that expression is going to look like this, where we have the derivative of f conjugate times the optimal residuals. So equivalently, what we have is the following, right? So d star is exactly d pi, and so if we move things around, we get that the f star derivative of the residuals with respect to q star are exactly these density ratios, measuring the ratio between the on-policy expectation for pi to our off-policy reference distribution. And this we can immediately use to do policy evaluation, because given these density ratios, we can just express the value of the policy as an expectation over our off-policy distribution of those density ratios weighted by R, right? And this just comes from important sampling, where the denominator here cancels with the expectation here, and you just get the on-policy expectation of rewards. Okay. To make this a little more concrete, we can think about what the objective looks like when our f function, which was our original, coming from our original f divergence, is just the square function. So when we start with the square function, its conjugate is also the square function. So we end up with this objective, this off-policy objective, that just tries to minimize these sort of Bellman residuals, square Bellman residuals, over our off-policy distribution. And what French-Rockefeller duality tells us is that if we've optimized this off-policy objective and we found a q star, then plugging q star into this expression, so now this is the derivative of f star, and the derivative of the square function is just x. So the residuals are exactly the density ratios. Okay, so this technique and sort of algorithm is dual dice, and that's from about a year ago. Now I'll take a brief pause, and maybe I'll leave this most important slide up, just because I understand it was a lot of math and maybe it'll take some time to digest. But yeah, just as a summary, the most important technique was here, where we started with this constrained problem, which is difficult to approach in stochastic off-policy settings. And what we did is we applied a convex objective to it. And that allowed us, when we take the French-Rockefeller dual, to get an unconstrained objective. Not only is it unconstrained, but by the fact that we chose the F divergence rather cleverly here, we ended up with an off-policy expectation here. And although these two problems are equivalent, the way they're presented is different, and the way this problem is presented specifically is much better for us. When we're in an off-policy setting, when we can only do stochastic gradients, when our state and action spaces are very large. Okay, hopefully that roughly makes sense. I think it'll become clear as we do more of these. But certainly, this algorithm for off-policy evaluation, dual dice performs quite well when you do it in practice, so especially when compared to this TD method, which is essentially dynamic programming. The convex programming approach performs much better, it's more accurate, and it's more stable. Okay, so now that we've talked a little bit about policy evaluation, let me show you how to do the same trick, but for policy optimization. So in policy optimization, we want to solve this problem. We want to find the policy which maximizes its value. And we know we have an expression for the value of a policy pi as this LP. And specifically, this is the dual of that QLP. So again, we have the issue that there's a lot of constraints here, and it's hard to deal with those constraints. Right? And we can think back to the dynamic programming approaches that I began by explaining. What they essentially do is they try doing the Bellman backups, and once you have an approximate Q pi, then you take a sort of gradient step for pi. But what we can do alternatively is try to circumvent these constraints by using the same trick of a convex regularizer. So what we're going to do is we're going to convexify this linear objective with the same regularizer, with the F divergence. Right, so here's a convex programming for the regularized policy value. Regularized with respect to this F divergence from this fixed reference distribution. And now that we have a regularized objective, so this is a convex objective, now when we apply Ofir duality, we're going to end up with an unconstrained problem. Right, so exactly the same as we had in the policy evaluation derivations. We now have this, the constraints here are moved to penalties, and these penalties are taken in expectation over our off-policy reference distribution. And now when we want to do policy optimization, all we have to do is put a max pi around this. Right? So if we do a max-min optimization with respect to pi and q, for this objective, we're going to eventually learn a policy which optimizes this regularized objective. Okay, so this is pretty neat. We can look at this, these sort of penalties and see that it's almost like what Q-learning and actual critic do, right? So we are learning a Q function to roughly minimize some convex function of the Bellman residual. But unlike Q-learning and actual critic, in our case, the expectation that we should be minimizing the square Bellman residual is an off-policy expectation. Right, and we can think back to dynamic programming approaches and realize, a lot of people do Q-learning and actual critic on off-policy data, but that essentially boils down to a very, very rough approximation, and it's unclear what that off-policy expectation is doing when you apply it to a dynamic programming algorithm. The nice thing about our setting, by using convex programming, convex duality, we're able to see where is this off-policy expectation coming from and why is it appearing. Specifically, it's appearing because of the specific regularization we employed here. And so now we can better understand that the off-policy expectation here is actually acting as a sort of regularizer on the policy, a regularizing that policy to be close to the off-policy distribution. On the other hand, in Q-learning and actual critic, you apply an off-policy expectation, and you have very little understanding of what it's doing, and a lot of times what it's doing is quite disastrous, right? There's all sorts of examples of applying Q-learning or actual critic in off-policy settings, and it just doesn't work and or diverges. In our case, the off-policy expectation is very natural, and it's clear where it comes from and why it's there. Okay, so this algorithm is known as AlgaDice, also from the past year. And so this is a nice off-policy objective for simultaneously learning these sorts of Q values and your policy pi to do off-policy optimization. Okay, and as a way of very brief look at results, if you apply this, it actually works quite well. So especially if you compare it to this actor critic here. Well, actor critic, you can apply it in an off-policy offline setting, but those rough approximations you apply to it are going to have consequences, and it'll lead to suboptimal convergence a lot of times. Okay, so again, let me try to slow down and maybe pause a bit on this slide. So this slide sort of summarizes the basic technique we've used so far, both in policy evaluation and policy optimization, where you can think of it as if we started from this original constrained primal problem in terms of Q values. We applied duality to put that in the dual space where we're optimizing for this D distribution. And because of this linear objective and constraints, which are hard to deal with, we applied a convex regularizer. And once we have a convex regularizer, then another application of duality puts us in the unconstrained primal form. And this is very good for us in cases where we have to use function approximation, where we have to use stochastic gradient descent, and all that. Okay, so that's a summary of the approach we've done, and at a high level, it is quite simple. And you can contrast it to what dynamic programming would do. Dynamic programming would start with this constrained, solve it directly, right? It would try to solve for these constraints by doing iterative Bellman backups to try to satisfy these all at once. Okay, so we're about halfway there. Looking back, what have we done so far? So we've started with the QLP, which characterizes the QPi values. Now the dual of the QLP involves the D distribution, and it characterized the on-policy dpi distribution. And we saw that if we apply appropriate regularization and then apply duality, then we were able to get problem formulations for policy evaluation or policy optimization that are especially amenable to off-policy and offline learning and don't have explicit constraints. Let's talk a little bit about downsides. Now, the main downside comes when we talk about policy optimization. So when we optimize for a policy, we still need that outer optimization over pi, right? We ended up with a max pi min q, which is a little undesirable or unsatisfying. Not only is it visually unsatisfying, the outer optimization over pi actually may not have nice properties. What do I mean by that? So we can think back to our original motivation, where we hope that by framing RL as a convex problem, we hope to be able to get better convergence guarantees. We hope to apply all these existing results in convex optimization. Unfortunately, when you do an optimization over pi and q simultaneously, you end up with an objective which actually doesn't have the nice properties you need, in the sense that it's not jointly convex or convex concave in pi and q. And I should emphasize this only happens when you do policy optimization. So like policy evaluation, it's fine because it only optimizes for q, it doesn't optimize for pi. But once you optimize for pi, you have these issues. Now what's the solution? It's going to end up being the VLP, which I referenced earlier in this talk. So the VLP is like the QLP, it's a linear programming, but it's more streamlined. It's more directly tackling the policy optimization problem. So we can recall back to this dynamic programming approach to policy optimization, which we're all familiar with, which is just standard max backup Q learning. So when I mentioned this in the beginning, I mentioned that it's no longer in matrix form, right? So this P star involves a max inside of it, and that means you don't have a linear operator, and so you can't easily express it in an LP directly. Now, the solution to this is to, instead of writing the LP instead of in terms of Q values, we write it in terms of the V values. Okay, so V values now are state values, and our constraints involve this transition operator, which is a linear operator. So the transition operator applied to V is the expected next state value, given that you're at a state and you apply some action. Okay, so what these constraints tell you is that the state value at S should be at least the immediate reward plus the expected next state value for any action that you choose on this right-hand side. What this means is that all these inequalities have to be satisfied, so V of S has to be at least the max over all actions of the immediate reward plus gamma times the next state value. And so what this means is that this is essentially expressing your max backup, and it enforces that your V star, your optimal V, has to be at least the optimal value function. And then the subjective in here is just going to push all these inequalities, or all these to be equalities, and your V star will be exactly the optimal state value function. And once you have the optimal state value function, then this objective, the expected initial state values, is exactly the value function of the optimal policy. Okay, so this is the primal VLP, and then the dual VLP looks like this. So it's very similar to the dual of the QLP, right? So we still have these D values, which represent a distribution, and the objective is the expectation under that distribution of rewards. The constraints look very similar, but now instead of describing the sort of stationarity of any distribution in terms of state and actions, it's actually in terms of states. So we have for each state, we have a sum over actions over here, and just the input probability density at each step to this state on the right-hand side. Okay, and the optimum of this will be the on-policy distribution of the optimal policy pi star. Okay, and now that we have this nice LP, we can immediately apply the same tricks we applied before. So if we want to do regularized policy optimization, all we need to do is we apply a convex regularizer to one of the LPs. So in this case, the dual LP. So I've added a KL divergence from some reference distribution. And now when we apply the French-Rockefeller duality, we get an unconstrained problem. Now the constraints become penalties, and they become penalties in the form of a log expected exponent. And this form comes from the fact that we chose a KL divergence here. So we can look at this and see, okay, instead of Bellman residuals, we now have a sort of advantage quantity here. And again, we're off policy, which is very nice for stochastic practical settings. One little problem is, once we've solved this, we have V star, but then how do we get the policy? How do we get back pi star from V star? So here again, we use French-Rockefeller duality, and which says that, okay, once we've solved this dualized problem, we can derive the solution to the original problem, which was the distribution, as this expression. And this expression comes from the log expected exponent form. And now this joint distribution over state and actions, we can condition it, right? So the optimal policy is just the conditional form of the state action distribution. And you can write that conditional distribution like this. And you can end up solving for pi star as a max likelihood optimization. Right? So this max likelihood optimization exactly matches pi star to be equal to this right-hand expression, the softmax. Okay, and this basic algorithm involving the learning V to optimize this log expected exponent, and then learning pi to do this max likelihood optimization is known as REPS, relative entropy policy search. Okay, so we've got this basic algorithm. What's good is that the optimization for V is now convex. We can apply all the standard convex optimization algorithms to approximate its solution. What's the bad? So one has to solve this second optimization problem to learn pi star. So this is sort of a bi-level optimization, and it's not as easy to understand, given that we're close to V star in the original problem. How close are we to pi star in this second problem that we have to solve? Another bad thing is that if we look at our optimization for V, it involves this expectation inside an exponent. And this expectation is an expectation over the transition operator. And typically in practical reinforcement learning scenarios, you can't actually compute this expectation. You can only compute a single sample, a single sample next state. So these problems lead us to this second form of duality given by the Lagrangian. So the Lagrangian is very related to French-Rockefeller duality. It also starts with this primal and dual problem, but it says don't solve either one of them, solve them both at the same time using this min-max optimization, where we take the objective from the primal for F, the objective for G star from the dual, and then have an extra term, linear term involving A and X and Y. Okay, and understandably, the result of this Lagrangian is going to be the result of either the primal or the dual, and the solutions are going to be the same under some mild conditions. So now we can apply this to the VLP and hopefully avoid some of those bad downsides I mentioned earlier. So the nice thing is with the Lagrangian, we don't even have to regularize anything, right? So we can start with the primal and dual LPs and just immediately write them in the Lagrangian form, right? So we took the primal objective here, we have the dual objective here, and then we have the A matrix involved here in the sum. So this is the Lagrangian. Immediately looking at it, it's not great. It's not great because of this sum. We want to turn this into an expectation. And to do that, we can just make a simple change of variables. So instead of thinking about this objective in terms of D, let's think about it in terms of zeta, where zeta is defined as the density D divided by some other reference distribution density. And now we can get the off-policy Lagrangian. So instead of a max over D, we have a max over zeta. Instead of a sum, here we have an expectation over a reference distribution. And we can bring this dual objective involving the worlds into this expectation as well. And now we can see that we still have this transition operator inside the expectation. But since there's no convex function applied to it, we can take that expectation outside, right? So we can combine the two expectations and just get an expectation over SAR S prime tuples of this sort of advantage function, single sample advantage function weighted by zeta. Okay, and that's the off-policy Lagrangian. It's very amenable to stochastic optimization, as we can see here. It doesn't have any of the downsides before. Perhaps one slight downside is you still have to do a minimum and a maximum. You also need to then do a second optimization to find the optimal policy pi star from your zeta star. But the nice thing is there is a lot of recent work that uses this objective, applies mirror descent or other convex optimization approaches to approximate zeta star and then show that given zeta star, your pi star will be provably near optimal. So this is great because this gets back to our original hope. Our hope that by using convex duality, by using convex programming, we would be able to leverage a lot of the convex optimization literature to get better convergence guarantees. And in this case, a lot of the convergence guarantees are actually sometimes faster than what the equivalent dynamic programming guarantee would be, especially when you think about in function approximation and stochastic settings. Okay, so that's a Lagrangian, and certainly, although I've only talked about it in the VLP context, it can also be applied to the QLP just as easily. And actually, that dual dice algorithm, which I started with, actually recommends using the Lagrangian over the Fenchel-Rockefeller dual objective that I presented. Okay, so that completes the main content of this talk. So we talked about the QLP, the VLP, how to apply Fenchel-Rockefeller duality, how to apply Lagrangian duality to get objectives that are more amenable to stochastic optimization and function approximation. So as a sort of summary and review, I'll just go briefly at the history, very roughly at a very high level, obviously, of all these approaches. So starting from the idea of duality, so linear duality, you may know it is relatively new. So it started maybe in the 1940s with Danzig and von Neumann, starting with like the min-max games. So that's linear duality. And then the idea of convex duality, as I presented it, started around the same time, maybe a little later in the 1950s. So that was all in the mathematical community. In terms of reinforcement learning, the idea of duality actually started with the VLP, which I presented later. So the VLP, which directly approaches the policy optimization problem, was started in the 60s and 70s. And at the time, they assumed full knowledge of the dynamics and rewards. What that means is that you can actually write the VLP explicitly. And once you can write it explicitly, you can actually solve it pretty directly using like the ellipsoid method. But you can't solve it when you don't know what the dynamics or rewards of your MDP are, when you only have access to stochastic samples. So a long time after the original VLP, I'd say maybe the use of LPs in modern times was sort of revived in the early 2000s from this paper, with this paper from De Farias and Van Roy, where they showed how to handle actual approximation errors in the VLP. So, you know, you can write the constraints down, but they're only going to be approximate constraints because you only have a finite sample of the transitions and rewards. And so far, that was all linear programming. The extension of the VLP to convex problems, so applying some convex regularizer, was maybe popularized around 2010 with Jan Peters using that KL regularization, which I showed, right, which yielded a log expected exponent objective. And then the use of the VLP in a Lagrangian form, all those, well, the most interesting recent work is just in the last few years and showing how to actually use that Lagrangian to learn near optimal policies with good convergence rates. So all this was in terms of the VLP. In terms of the QLP was mostly overlooked. And as far as I know, maybe the first explicit use of it was just like in the last 2 years, starting with dual dice for policy evaluation. And this basic technique was then extended to policy optimization and imitation learning as well. And if you're interested in reading more about this, so the distillation of the QLP as well as some writing about the VLP is on archive from myself and Bo Dai. So that's the past. And now, what does the future take us? Where do we go from here? So I'll list a couple of things which I think are interesting, but certainly there's a lot of potential avenues for future work. So perhaps the most prominent thing in my mind is this original hope we had. The hope for convex programming to yield better convergence guarantees and better algorithms. Now, we can see from this presentation that this was only partially satisfied, right? So specifically for the QLP when you only do policy evaluation, and for the VLP when you only use the Lagrangian. And this naturally presents a lot of follow-up questions like, are there convergence guarantees possible when you do policy optimization but with the QLP? Or are there guarantees for the VLP but using the Fenchel-Rockefeller duality instead of this min-max Lagrangian? That's one direction. Another interesting artifact of existing work is that in terms of practical performance, the QLP usually performs much better than the VLP. Even though, in policy optimization, the VLP seems to have better theoretical guarantees. So it's a lot of, it's a big open question for me whether there are better practical instantiations of the VLP to actually match or improve performance over the QLP-based methods. And then lastly, the applications of duality to RL that I think are known are pretty limited. And I think there's a lot more potential applications of duality to other aspects of RL, maybe in terms of apprenticeship learning or multi-objective learning or learning RL with constraints and safety and risk sensitivity that I think are very interesting to explore. Okay, and that completes my presentations. Thank you for listening, and see you soon.
So that was a great talk, and Ofir is still around to answer some of your questions live. If you'd like to ask him a question, I think he's gonna join us back in a second and turn on his camera.
Hey.
Hi, Ofir. So I think you answered a lot of questions already. I look in the Q&A, and then there are 13 answered questions. 3 of them are open. So if you want, you can either read some of these questions that are in the Q&A, or we can also take live questions from the participants. That's possible if the participants use the raise hand feature. So it's up to you.
Yeah, I'm open to both. I guess we can start with the written Q&A as we wait for hands.
Sounds good. So we have 2 hands now, but you can start with the Q&A.
Okay, we'll do one question on Q&A. So Evgeny asks how well these techniques perform empirically compared to other off-policy eval or control methods. So empirically, at least the published results, and most of these results I think were published a year ago, in terms of off-policy eval, the convex programming approach does much better. In terms of off-policy control, like policy optimization, the convex programming approach only does competitively. So there's no clear gain, but there's no clear loss either.
Would you like to take a question from a participant?
Yeah.
That's good. So I think if the CIFAR team can unmute Tolga Akhtas.
Hello, Ofir. Thanks for the presentation. It was a very interesting subject. I think I did see how the math. Can you hear me?
Yeah.
I think I saw how like the math builds up from this initial step of finding the duality, but I think where I'm stuck is roughly around there. I did ask earlier, but I didn't quite understand. One is that there's this idea of finding dual problems, not only in this, but even for support vector machines. I remember seeing that, and even then I was confused. What's the deal with that? Why do we find dual problems? I'm guessing it makes life a little simpler in terms of solving the problem or offering some guarantees. And the other is, table seems like a pretty deterministic thing, but distribution is kind of feels like a probabilistic thing. So I didn't quite see how we transition from one to the other. Thank you.
Yeah, so to the first question, yeah, so I guess the question is generally, why does duality help? And yeah, I think that's a tough question to answer. I guess in terms of, well, what immediately comes to my mind is duality is a way to see problems from a different perspective, in the sense that if you start with a primal problem and turn it into its dual problem, it's actually the same problem. It's just presented in a different way. It's like a different lens, or it's almost like looking at a reflection in the mirror. And in some sense, there shouldn't be a benefit because it's the same problem. But in practice, what it allows us to do, I guess it allows us as people, like as humans, to change our perspective on a problem. Like it's essentially like when you look at the dual problem, it's still the same problem, but I feel like it helps a lot in the sense of giving you a new perspective on the problem. And like in our case, the new perspective is, for example, the typical way to do policy optimization is by thinking about Q values. But another way to do policy optimization, which is less typical and less natural, is by thinking about the distribution over states and actions. And that different perspective can be very advantageous to be aware of, as we've seen, in the sense that once you think about distribution or policy optimization as an optimization of state action distribution, then you can think about, well, a natural regularizer for that is like an F divergence of your learned distribution from your data distribution, and that regularizer is very natural and leads to all these nice properties down the line.
So if you want, you can take more questions from Q&A. There are two other questions.
Okay. So Ming Xuan asks, could you talk about how you got this idea? I really like those old theoretical ideas before the DLRL era, but how can we find those interesting ones? So the genesis of this idea was actually not from thinking about convex duality. So actually, my first paper in this area was the dual dice paper. And actually, if you look at the dual dice paper, although we use the word duality, we don't actually use convex duality as I've presented it here. What we actually do, we call it like a change of variables trick, which is essentially the same thing, but we actually derived it from a very different view. And so, yeah, in terms of convex duality, we only realized we were doing convex duality and Fenchel-Rockefeller duality specifically after the fact. So at the time, I guess it was indeed some sort of random search. We were just sort of playing around with these quantities. We were aware of like the distribution perspective of policy optimization, and we did think it was interesting. And at the time, we were just sort of playing around with it to see what we could do, and we ended up with the dual dice paper. I can keep going down. So those are questions from Angelo. Are there any works exploring convex duality in a model-based setting? If not, what would be interesting first steps? So in a model-based setting, there are some works which you could say do this. At least in my mind, there is a recent work from Gergely-Noy that looks at model-based uncertainty in the sense of sometimes people do exploration by learning optimistic models of an MDP. And those optimistic models, you can, well, that problem you can frame as a constrained problem, which is not exactly convex, but it's close to convex. And there is some work, this recent work from Gergely Noy at, even though it's not a strictly convex problem, it's still a constrained problem. And you can actually still derive its dual. And the dual actually gives you a new perspective on model optimism as value optimism. And value optimism ends up being the typical count-based exploration people use. So that's a work I know of, and it's in my head right now. Maybe those others, which can also be described as model-based, but certainly there's a lot more stuff to do. So yeah, the work I know is just looking at exploration, but maybe those ways to write what model-based RL as a convex program.
Thank you. So I think we have a tiny bit more time. So if none of the participants want to ask a question, I would have a question. And so if you remember, actually on Wednesday when Adam gave his talk, he mentioned this question of the deadly triad. And in a way, what Ofir has been presenting today offers some solutions to at least two of these problems in the triad, which is compatibility with nonlinear function approximation, as well as the off policy aspect. And so my question for you, Ofir, is is this approach a solution as well to bootstrapping? Because does it deal with bootstrapping?
Yeah, I think I would agree that the convex programming approach does in some ways solve the bootstrapping problem, because you're no longer doing any bootstrapping. You're actually doing like some sort of residual gradient optimization. At the same time, you could say that it introduces its own problems. Like there's a few recent papers that I think look at, for example, the Lagrangian of the VLP, which has these nice convergence guarantees, but then make an important finding that those convergence guarantees actually rely on specific properties of the function approximation class. And if you look at those properties in detail, they're usually not satisfied in practice. And so it presents its own problems, which, well, yeah, you never get a free lunch.
I see. So in a sense, you don't have the bootstrapping issue because you don't use it in the formulation, essentially. But if I remember correctly, you did have this reward plus gamma value term in there. So this is already a form of bootstrapping. Do you think that you could recover an unconstrained formulation in which you have more than a one-step bootstrapping? Do you think there could be a way of, let's say, recovering a lambda style bootstrapping instead?
I think, yeah, I think it should be feasible. What it would have to do is that you would just have to switch your constraints in the original LPs to, instead of being about single steps, to be about multiple steps. And I think it certainly is feasible, although it does get messy. I'm sure there's a clean way to do it, but at least there is a messy way to do it where like you can blow up the number of constraints. Instead of like having a constraint for each state and action, you have like a constraint for each k-step state and action sequence. And that can get messy, but it certainly feels feasible to have a multiple step constraint and then translate that to a multi-step return in the final objective.
Sounds good. Thank you so much, Ofir. I think this is very exciting, and I'm really excited about the future basic level